And I said, yeah, why not? You know, like people have done that before. And he said, I don't believe that. But then he said, don't trust me, I've become an old man now. Anyway, my comment to that 10 to the 500 is that this idea that the theory determines a solution to the theory is not very common in physics. You know, like there are equations and then there are solutions, right? Okay, so you can have it. I think getting the equation right is a good step. I think it's a very important step. I think the hope has been that, and I believe, I think somebody mentioned this hope actually was, in a sense, initiated by Einstein, who believed that there would be unique solutions to field equations. I mean, not just any solution, but unique solutions. That hope was maybe a bit too much. I mean, I don't know whether that or not true, but so maybe the part of string theory which has got to do with you know, unification of fundamental forces. I mean, it's, as a theory of nature, that in that sense, I think that might have to just go the way other theories went. You know, you do some theory, then there are experiments. It gives you some clues about, you know, what are the, you know, how did we know that SU3 was the gauge group of QCD? I mean, any SUN is a consistent theory. Nobody ever thought of saying that, knowing that it's a Young-Mills theory will determine that there are three colors, but we still know, but that's a phenomenological fact. And sometimes things might come surprising. I mean, theoretically, nobody thought before, say, 1995 or 96, that one would be able to understand black hole as microscopic objects in some theory. I think people thought it's something very mysterious, black hole entropy and, you know, stuff like that. Well, it just came, right? I think we now think that string theory is very far away, and I think Cliff has already mentioned this, that but we don't know what the string scale is, and if the bisect data actually survives, or some version of it survives, we might have to ask questions about that scale. You know, maybe cosmology might be giving us clues to that scale, and maybe something will be determined. So I don't rule it out. The fact that all I meant to say that is that, you know, the hope that the equations uniquely determine the solution, that philosophy may be not right, but you might still be able to make it, I think.
Cliff has something to say about landscape, or should I hand you back? Oh,
I
okay.
kind of always never, in the 80s, I remember thinking that string theory has a lot of degrees of freedom, so there's probably going to be a lot of solutions to it, and I never really understood the argument that said that they're all going to go away. Because if they're all going to go away, you would have thought the one that will survive will be flat 10-dimensional space, and we don't like that one. So, yeah, I kind of, the idea of there being a landscape never really seemed that disturbing, and I always kind of thought that it wasn't really Ed Witten that did it to us, it was Einstein that did it to us, because normally, if you say that in electromagnetism you have lots and lots of solutions, you would then say, well, what we want is the vacuum solution, and we use energy as the criterion for choosing one. And then the problem with generally covariant theories is that energy conservation, or everything's got zero energy, and so you can't really use energy as a criterion. But if you go back to the theories that we would have said didn't have a landscape, like say electromagnetism in a gravitational field or something, we tend to throw away solutions we don't like. Like we don't have to have, even in four-dimensional electromagnetism coupled to gravity, we don't have to look at the four-dimensional vacuum. We could have looked at a two-dimensional vacuum where a vacuum where two dimensions are large and two are small. And we didn't really think about it too much before. I think the string theories have just forced us to think about it. So there are landscape issues, and I think that you have to distinguish the landscape from the Bay Area landscape, because I think that the Bay Area landscape has a very hardcore anthropic overlay, which I think we don't necessarily have to buy into. But the general problem of how you predict things with a lot of solutions probably will go back to, I think I agree with Sumit, that's probably a series of conditional statements, that if I'm living in a world where the universe has been expanding, and then I find that this is true, then I should expect that to be true, and it's not going to be absolute statements, it'll be conditional statements. And And I think the practical problem now is not that we have so many solutions we need to worry about their statistics. I think the problem is we don't have one solution that looks like the world around us. And the hard part is finding them, and given there are so many of them. And so I think we're really have a problem of identifying solutions rather than worrying about the statistics of them when we found them. You give me two solutions with a standard model in it, and then I'll start worrying about the statistics they have, but until you give me two, I'm not so worried about the statistics.
I thought you found one solution, this quantum Hall effect.
Oh, yeah.
It's the same theory.
I meant kind of the standard model and everything.
I think that drives up to a point that it's good that we have a landscape. It's very good because then this tells you that string theory is applicable to a huge variety of phenomena and not just some questions. So I view it very positively actually. I just don't subscribe to the philosophy that actually.
I have nothing deep to say except it's nice to have a belief, have some faith in something, but you don't have to tell people. So I start up train and taught and believe that there will be unique theory. But at given time, the facts speak for itself. There are a lot of things going on. So you have to accept that. But it doesn't hurt to believe there will be unique. So things may come along. So, as far as the string, to answer what string theory might do, let me just tell a story. Having been trained as a graduate student, believe in having an ultimately unique theory, determining everything, including the QCD is SU3, right, not SU4. But when I was a postdoc at Princeton, I spent a summer at Brookhaven. Brookhaven is a place where people get together, condensed matter, particle physics, we all have lunch together. I think one day a condensed matter theorist told me, the whole world everything is critical phenomenon. That was an eye-opener for me. Okay. Finally, I learned something from the condensed matter theorist, which normally I just ignore, but got me to think a lot. Everything at the time is just effective theory, and everything can be understood in terms of critical phenomena, sort of losing of scale, or lack of scale, or lack of all scales. And so if you start thinking that way, you open up your mind quite a bit. So strings theory allows us to open up our mind as well, and perhaps free ourselves from the constraint of limiting ourselves to certain renormalizable local field theory, and but yet everything makes sense, and then you can think more broadly, and at some point you can redirect yourself within the new directions.
Maybe we don't say anything, they're okay. Right, so. Any more questions? I found,
What do the
students.
young people think?
Yeah, what do young people think? I mean, what's the young for that? I mean, yeah, we could do with some questions from the young audience. The truth is that why else do you come here? If you don't have a question. Yeah, well, do you want to shout or do you
Yeah,
want to?
I'm not a student, but I'll ask a question. So
Okay.
a lot of successes of the second superstring revolution revolved around those dualities, right? And I know that it's really, really hard to get considered vacuum in string theory, but given that we have so many, like for example, we have a lot of models of cosmology in type 2B, and it's very hard to get models of cosmology in type 2A. So shouldn't there be some duality and variant physical predictions in some of these models? Like, is there any work in that direction, or any hope in that direction?
Or somebody, Chris, or like, you want to comment on it?
You're wondering, what's if there's the type 2B solutions, then there should be duals of them somewhere.
Just generically, if there's some duality to the overarching framework of the theory, shouldn't there be some duality and variance in the predictions of the theory?
I don't know, that's a good question. I guess I'm not really that.
I think you say that there are so many duality in the string theory. So invariant formulation.
Oh, duality invariant formulation of the theory.
What I mean is, okay, maybe, but it's more what I mean is like, so if I give one of these really complicated stringy models of early universe cosmology in one theory, and shouldn't I be able to find the same prediction in another theory that's accessible by some duality transformation, even if it's really hard? I mean, I guess, wouldn't that be the natural place to look for viable models? Something that...
Yeah, I think maybe the issue is that, yeah, I completely agree. There should be another solution in the other theory. I think the problem with finding things like de Sitter vacuum and all that is the problem of controllable calculation. Like in one duality frame is a controlled calculation may not be a controlled calculation in another duality frame. That things can become very stringy. At the end of the day, we know so little about string theory, and we know so few string theories really speaking, that we always end up trying to work our way to go to a corner where we can avoid string theory. So that we can talk about supergravity and things like that. And that's what poses this problem of going to a particular frame and trying to find it. Yes, sure, there is a solution. We have no idea about. I mean, in all this, we call them compactifications of string theory. They're really compactifications of supergravity, because that's the only thing which we really know. So, it has become an art just to find out, go to that right corner where you can control a calculation. And even then, as you know, I mean, even for the de Sitter vacuum, there's a lot of controversy whether that calculation, the KKLT calculation, is really well controlled or not. There are anti-brains and there are antipoles, all kind of stuff in it. But I think it just tells you, it might tell you two things. It might tell you that, one thing it tells you we don't know string theory, what it is really. And the second thing it might tell you is that, what we call string theory now is, I don't know, 20 years down the line could be quite irrelevant. I mean, it may be a completely different bag of things which are, in my slides I said that, I believe that ADS-CFT or holographic correspondence something is probably here to stay. I'm not convinced how much it's got to do with string theory really. Like it came out of string theory. It's very much like in the 70s, like in Chung-I just mentioned that renormalizability was a big thing. You have to go to renormalizable quantum field theories, and great things was discovered. The theory of electroweak interactions was discovered, the theory of strong interactions were discovered, and then somebody comes and teaches you that it's not a big deal after all. Like everything. I mean, in fact, either theories are automatically renormalizable or just not there. So I think string theory could be one of those things. It's one of those things we're just looking for, this microscopic thing. We find a rich array of right things, and then we realize that we can get rid of it. So who knows? I don't know. I have an open mind about it.
One point there is that the history of physics is littered with successful theories whose original motivation was wrong.
Yeah.
Could mention the story that John Schwartz was bothered by the question that there are so many different string theories at that time. So I want to ask you guys, what problems in string theory that are bothering you the most? Such that they might give me some hint about what the next revolution might look like.
I'll answer I don't know if I answered it.
It bothers me about supersymmetry.
Yeah. I would sort of agree with that. It also bothers me that we don't know what string theory is. We know worldsheet formulations of a certain class of theories, which are all highly supersymmetric, which played a very important role in our thinking, but could be completely irrelevant for all we know. Or maybe it's something very fundamental for description of gravity. So I think that's why I think well, at the cost of not getting a job, maybe people should work on string theory proper. We're trying to get a formulation, but I don't know. But I think the things which are taught about gravity, particularly about black holes, I think are going to stay. And I would like to believe the next thing we will learn about gravity will have to do with cosmology. I think we probably learn something about it. Pretty confusing at the moment, but I think the next big another next big revolution of it will come from there.
See, the only problem we can solve as physicists is harmonic oscillator. The question really is how, well, okay. The question is how can you perform some magical transformation so that you can solve it as a harmonic oscillator. Okay. So once you get to that level, you don't have to worry about the really truly complicated. But the question is how to get there. Yeah, who knows? Some young people will figure it out.
And also I think a lot of interesting physics is not about exact solutions. A lot of interesting physics has got to do with approximations. So harmonic oscillator is the basic thing which we approximate things with, and then we work around it. We don't know the analog for that with supersymmetry. We don't know, starting from a supersymmetry, what should we do? The next step. And I think that's independent of string theory is something. When Cyber-Witten came, I think there was a lingering hope that we will understand that this is the base, and we start from there and we understand non-supersymmetric gauge theory. It would have been fantastic. But it looks like things are pretty tied down to supersymmetry there. So, I think there's something to be learned there. I don't know what it is.
Yeah, I guess my question just now was actually related to Junwei's question. Is like, let's say if you could make one wish to string theory God, what would you make? If you have more than one wish, that would be even better. Or basically, like one problem you want to actually, okay, maybe more concrete. Like in the next, for example, like I have my own personal vision. I think A equals 4 young meals is going to be solved in my lifetime, knowing all the correlation function. That's something I can see coming in 25 years. Is there something you can see in 25 years that actually been solved, like in high energy theory in general? And yeah, I mean, somebody can say something.
I just wish that the bicep data will be correct. Because this will be the first time we'll get some inkling that there's something called quantum gravity. After all, these are things which are quantized, though weakly coupled gravitational waves in an inflationary background. So I think it will be fantastic if that is correct. I think it will force us to think more about quantum gravity, string theory or not.
So you do have a wish.
I don't want to have a 25-year for I have a shorter term hope. Hopefully somebody will help solve the problem.
Okay.
I wish somehow we can do NTU-CTP with symptotic freedom delta properly.
I see. Good.
Can you repeat the question?
Oh, basically, like if you have one wish or one problem you can see solved in in your subsequent research career in string theory. Cosmological constant.
Yeah, that would be good. I got a punch on it. I have to think of that more.
Okay.
Oh, my hope would be to see a really successful application in condensed matter.
Okay. Maybe you do have a wish.
Okay, so I think what's really missing in string theory is we need a new understanding so that the theory is, motivated by itself, like a symmetry principle or something. Right now, everything is very technical and where we solve coincidences or magics, and we're inspired to learn new relations. But I think what's really missing, and ultimately we need to make this progress to understand string theory from a new viewpoint, so that you can understand perhaps ADS-CFT more conceptually. So that, just like how you understand general relativity, if you are given the Einstein equations in component forms in an expansion around the flat background, it could look just horribly complicated, but when you calculate, you are going to see a lot of coincidences. So I think I would like to see the analog of equivalence principle or something like that with string theory.
I don't know. I don't know if I have a well articulated one.
Okay, that's fine. So, any more questions from the audience? Okay, so we are down to the last 5 minutes. So I guess if each of the panelists can give one piece of, I don't know, not even advice or message for those of students who want to go into time theory in general, like now at this moment. Yeah.
Like career advice.
Usually that's a bad thing to say, right? But just one piece of from your personal experience, you think something might be valuable for the people who just got into grad school. Like.
My advice would be don't listen to anything people my age say.
There's a paradox there.
Assuming you have a piece of it.
When you become a graduate student, you always, at the end, wind up focusing on a very narrow problem. You become very good at it, and you solve it, and you're making progress. My advice is, while you're doing that, keep your eyes open about other things. You can't do everything, but yet you should pay some attention to what's going on. And of course, it's easily said than done. I can't, looking back, I can't say that I have done that properly myself. And but it helps to keep open mind on a lot of things.
And I'll just reiterate what Chung-I said. I think one of the things string theory has taught us is the unification of knowledge. Maybe not unification of theories. And I think I started my career trying to learn about confinement, and right now I'm trying to learn about to apply ADS-CFT to understand non-equilibrium critical phenomena. So I think yes, keep an open mind and treat theoretical physics as theoretical physics, without pigeonholing them. I think that's enough for now.
Yeah. So I think unless panelists have something burning to say or like to vent. No. Okay. Then I think we should thank this brilliant effort this afternoon.